Let us start the lecture. In this lecture, we are going to discuss about the spectral series of hydrogen atom. We already discussed about the expression for radius, velocity, energy and wave number. In this actually we have to use the expression for wave number. As we know, the expression for wave number is our 1 by lambda is equal to rz square 1 by n1 square minus 1 by n2 square. Here as we take hydrogen atom, so we have to put z equal to 1. So this becomes 1 by lambda equal to r 1 by n1 square minus 1 by n2 square. So, other than what is this lambda actually? As we know, when electron jumps from higher orbit to lower orbit, then it must emit some energy, and we know that energy is our h nu. Actually, from that h nu we can find the lambda, value of lambda, wavelength of radiant energy. So, after then this r is our Rydberg constant, and the value of this Rydberg constant is our 1.097 into 10 power 7 meter inverse. Yes or no? After then this n1 is our lower energy level, remember this one, and this n2 is our higher energy level. Okay, and just remember some few things. For shortest wavelength, we have, if you have to calculate the shortest wavelength, then we have to put n2 equal to infinity, and for the longest wavelength we have to put n2 equal to n1 plus 1. Actually we have fixed n1 values for different series. Okay, then only we have to change the n2 value. After then we have to start the spectral series. What we have, first one is our Lyman series. Actually this Lyman series is our the spectral series obtained when an electron jumps from any higher orbit, that is you can take 2, 3, 4, 5, 6, so on, to the ground state. That means here we have to take n1 equal to 1. Then higher energy levels we have to take n2 equal to 2, 3, 4, 5, 6, so on. Okay. Then our expression for wave number becomes 1 by lambda r 1 minus 1 by n2 square. Here you just put 1 in place of n1. Okay. Then if we have to find the shortest wavelength, then we have to put n2 equal to infinity. Okay. If we put n2 equal to infinity and calculate the value of lambda, then you can get lambda s shortest value is equal to 91.175 nanometer. Then if we have to find the longest wavelength, that means we have to find the wavelength range of Lyman series. If we have to find the longest wavelength, so we have to put n2 equal to 2, as we have n1 equal to 1. So for longest wavelength, n2 equal to n1 plus 1, and here you can get n2 equal to 2. Then we can get lambda is equal to 1 to 1.57 nanometer. And you can see this wavelength range lie within the ultraviolet region. As you know, in ultraviolet region the wavelength range is our 1 nanometer to 400 nanometer. As this lambda s and lambda l lie within that region, so here you can say that Lyman series lie within the ultraviolet region. Yes or no? After then we have Balmer series. Then what is the Balmer series? Actually the spectral series obtained when an electron jumps from any higher orbit, that means here higher orbit starts from n equal to 3, 4, 5, so on, to the second orbit. That means here we have to take n1 equal to 2 and n2 is our 3, 4, 5, 6, so on. Okay. Then our the expression for wave number becomes 1 by lambda r 1 by 4 minus 1 by n2 square. In place of n1 we just put 2, so the square of 2 is our 4. Yes or no? Then if here we have to find the lambda s and lambda l value, to find the shortest wavelength we have to put n2 equal to infinity. Then you can get lambda s is our 364.7 nanometer. And if you put n2 equal to n1 plus 1, that means here we have to put n2 equal to 3 for longest wavelength. Then you can get 656.3 nanometer. Spectrum actually lie within the visible region. As you know, visible region lie within 400 nanometer to 700 nanometer. Actually here you can observe that lambda is our 364.7, which is not in this region. So actually most of the wavelength of Balmer series lie within the visible region. So here we take the Balmer series is our visible region, but few wavelengths comes to the ultraviolet region actually, as most of the spectral lines lie. So here you can say Balmer series lie within the visible region. Okay. Then for fast line, or we can say also H alpha line, fast line means we have to put n2 equal to n1 plus 1. For second line or second member, we have to put n2 equal to n1 plus 2. Similarly, for third member, we have to put n2 equal to n1 plus 3 and so on. Actually, first line is called, the first line of Balmer series are called H alpha line. So here we just put n2 equal to 3. Then you can get lambda 1, first line is our 656.3 nanometer. And for second line, that means if an electron jumps from n equal to 4 to n equal to 2. When electron jumps from 3 to 2, then this is our first line or H alpha line. When jumps from 4 to 2, then this is our second line, or you can say H beta line or second member also. When it jumps from 5 to 2 or fifth orbit to second orbit, then you can say this is our gamma line or third member, third line you can also say. When 6 to 2, we can say fourth member or fourth line. Okay. Then for H beta line, we can get lambda 2 equal to 486.1 nanometer. Then H gamma line, we have to put n2 equal to 5, so that we can get lambda 3 is your 434.0 nanometer. And H delta line is our lambda 4 is equal to 410.2 nanometer. You can observe here most of the spectral lines or wavelength of spectral series are lie within the visible region. So we can say Balmer series lie within the visible region. Okay, but few lines comes to the UV region actually. After then we have Paschen series. So here we have to take n1 equal to 3, and higher energy level starts from 4, n2 equal to 4, 5, 6, so on. That means here electron jumps from any higher orbit to the n equal to 3 orbit. Higher orbits minimum starts from 4. Okay. Then our wave number expression becomes 1 by lambda is equal to r 1 by 9 minus 1 by n2 square. n1 square, n1 we just put n1 equal to 3, so this becomes 1 by 9. And then here we have to find the wavelength range, so that we can say in which region it can lie. Then if we put n2 equal to infinity, for shortest wavelength we can get 820.4 nanometer, and for longest wavelength we have to put n2 equal to n1 plus 1, so that we can get n2 equal to 4. For that we can get 187.2 nanometer, and we know as the 820.4 nanometer, 1875.2 nanometer, these all lie within the infrared region. As in infrared region, we have the wavelength range starting from 700 nanometer to 1 millimeter, actually 1 mm. Okay. Similarly, after then we have bracket series. In bracket series we have to take n1 equal to 4 and n2 equal to 5, 6, 7, 8, so on. Then the expression for wave number becomes 1 by lambda is equal to r 1 by 16 minus 1 by n2 square. Okay. Here also you have to put the n2, you have to put n2 equal to infinity, so that we can get the shortest wavelength. This becomes 1458.5 nanometer. After then if you put n2 equal to n1 plus 1, that means here we have to put n2 equal to 5 for the longest wavelength. Then you can get 4051.4 nanometer. These also lie within the infrared region, 700 nanometer to 1 mm actually. After then we have Paschen series. Then here we have to take n1 equal to 5, n2 equal to 6, 7, 8, so on. So that our wave number expression becomes 1 by lambda is equal to r. In place of n1 we can put 5, so that this becomes 5 square is equal to 25. 1 by 25 minus 1 by n2 square. After then we have to put the value of n2 as infinity, so that we can get the shortest wavelength value. Then this becomes 2279 nanometer. After then lambda L is our 7460 nanometer. This wavelength range also lie within the infrared region, which is in between 700 nanometer to 1 mm. Yes or no? Actually these are the spectral series we have in the hydrogen atom. Then remember note point, number of spectral lines obtained when an electron jumps from n2 to n1. n2 is our higher energy level, n1 is our lower energy level. So how many spectral lines are obtained? So the formula for that is our n is equal to capital N is our number of spectral lines obtained is equal to n2 minus n1 into n2 minus n1 plus 1 by 2. In place of n2 minus n1 you can write delta n also, change in n. Okay. Then just remember few things. Some questions are asked just like this. Find out the wavelength of first member or first line of Balmer series or second member of Lyman series. So how you can find that? Just remember this one. As we know, for each spectral series we have fixed n1 value. So we just have to take the n2 value. Okay. For first member or first line we have to take n2 equal to n1 plus 1. Similarly, for second member we have to take n2 equal to n1 plus 2, for fourth member n1 plus 4, for fifth member n1 plus 5, and so on. Yes, this is all about the lecture.